Heavenly Father, thank you for your loving kindness that's happening even now in this room. In fact, all over campus. In fact, all over this world. And Lord, there are people going through a lot harder times than we are, but nonetheless, we're here by the grace of God, and you can work in us, even in a class like this, and bring something real out of it so it makes a difference in those around us. And I pray you do that, Father. I pray you would just exercise your amazing grace right here. In Jesus' name, amen. Okay, so I want to, oh, rats, we fucked it all out. Okay, I want to do this. So this class, this was response to a question I got. So my class lecture, what I'm doing now, is designed to supplement the text. I mean, there are some teachers that have you read the text, and in class, they read the text, and that's what you got. You got to extract the information from the text. Well, I have the text. I've read the text. I've read it more than, well, it doesn't matter. So I've read it. So what my lecture does is emphasize what I think is important, because everything in this book is not important. Some of the stuff is bogus, even. I mean, the creation stuff, the cosmology, that stuff like that in there, a lot of that is just bogus. But nonetheless, I want to emphasize what I think is important and where needed to clarify what's stated in here. So the text questions, the things that I'm asking you to turn in, they're designed to encourage the reading and study of the text. If I didn't give them to you, well, if you're like any students, there are a number of you that probably wouldn't bother to read it. In fact, the videos that I post for the async class, there are not many people that read them. I mean, you know, they wait for a study guide.
Yeah.
They can do the test mechanic, they can do the questions. I mean, they guess they have to read them, but they don't have to watch anything until they get the study guide and then study the study guide. I mean, I was a student, I can figure out how to avoid making an effort. But the text questions are designed to encourage you to read and study the text and to expose to me, when I grade them, what's not understood by the class. So I do that in my math class. I give an assignment. And I want the assignment back before the class the next day, so that when I look at that, I can see, oh, okay, so a number of people are missing this thing. So then I can emphasize that. If nobody's missing it, then I don't have to spend time going over it again. I can just go on to something else. So that's how I process math, and that's how I process this. You turn these things in, hopefully by Monday, I have these, well, I will have these graded, but I try to get, you turn them in, then I turn them back to you the next time we meet, and I can talk about them. You can see what you didn't get, and hopefully by going over them, you can supplement what you did and say, oh, you put this down or put that down, and then you'll be better equipped when it comes to test taking. So, and these aren't, as far as your grade's concerned, these are the least costly as far as an impact on your grade, whereas your tests are more. So to use these as a platform to do your study guide or whatever, I think that's why I do it this way. I could give the lecture and then have you do the test questions, but then if a lot of people miss something, then I would need to go over that a third time, and I just don't have time in the class to do that. Mm-hmm. This is a 1 semester, non-lab science class. I mean, we're talking a sweep and a promise. So to go over it, and then go over it, then I grade it, and then go over it again. I don't have time to do that. So, that addresses at least somewhat what the question was asked about this. There is a reason for doing it. If you're dissatisfied with that, then you should put that when you have an opportunity. In fact, I think they've opened it up for that already. So you have an opportunity to write that down. And I have changed the way I teach in some of my classes. I've changed the way I do things because of the constructive criticism about what I was doing. I mean, while I would like to change my personality to some degree, I'm kind of stuck with that, and so are you. But as far as how I do things mechanically, in my prayer class, I've engaged more in dialogue about things because of students wanting that. So I can make adjustments in what I do. And I'm willing to. It's not that, well, this is the only way I'm ever going to do it. I've changed because of comments. So the comments are important. If you see something that you think would be better for you or for others, or doesn't matter, just put it down. Take the time to write on that stuff. Because it has an impact on me. I change to accommodate. But you're going to find in any class like this, you're going to find people different. Some people don't like the subject, so they have to take it, so they have a different perspective on it already, and everybody teaches differently. Tom Lorimer is a great teacher. I've had him for classes. I think he's a great teacher. He could teach at any level. I haven't had David Bagby, but being with him in meetings and just the volume of knowledge that he retains, I mean, wow. But everybody's different. And there have been people weirder than me teaching. So, just saying. Okay. So I'm going to go ahead and go over this. This number 12, when I turn back. Okay. Some of these are very simple. Some of them were kind of tricky. I didn't realize there was something. Part of the class, as well as most all the async class, got questions that had all the information in them. But some of you didn't. I don't know how exactly that happened, but anyway. What happens to air when it's compressed? Warms up. So we're talking, this is adiabatic stuff, this is air pressure stuff. So what happens to air when it's compressed? It heats up. What happens to it expands? It cools. So when it rises, and the counterintuitive thing is you think when it rises, when things rise, usually they get warmer. But in this case, when it rises, it gets cooler because it's less air pressure. So why does air cool when it rises? Air pressure decreases as the altitude increases. So as you go up, the air pressure goes down. As you get higher, there are less molecules pushing on that thing, there's less pressure. So decreased air pressure allows the air to expand, and as it expands, it cools. What's the constant rate of temperature change for a parcel of unsaturated air? So it's unsaturated. It's unsaturated. It's not full of, it could have a lot of moisture in it, but it's not full. It's not saturated. 10 degrees centigrade for every 1,000 meters. Going up and coming down. So every 1,000 meters going up, it loses 10 degrees centigrade. Unsaturated. Every 1,000 meters going down, it gains 10 degrees. So it's both ways. Unsaturated. So that doesn't mean, well, it goes up until it's the condensation level, and that's when it's saturated. So then it changes. But up till then, it can go up, every 1,000 meters it gains, or it loses 10, and as it goes back down, it gains 10 every 1,000 meters. So, So there's Earth. And let's say up here was the condensation level. So, but all the way up here. So if you have a package of air and it starts off at, let's say it starts off at 30 degrees centigrade here. It goes up 1,000 meters. So this is going to be then 20 degrees centigrade. It loses. It cools. Then you go up here and it's 10 degrees centigrade. And then it goes up here and it's 0 degrees centigrade. So every 1,000 meters it goes up. And let's say something came in and it went and it turned around and then you're going down like this. So you go from 0 degrees to 10 degrees. It warms up. Here it's cooling. It's cooling. When it's going this way, but it's warming when it's going this way. So if this air sometimes drops 1,000 meters, it goes down. When it drops another 1,000, it goes down. When it drops another 1,000, it gets back to where it started from. Okay? So it can gain, this is all unsaturated. Saturated is up here. We haven't gotten to saturated. It's all unsaturated. So as it rises, it cools. As it descends, it warms. So it's going up and coming down, both of those things. If you didn't put both of them, you lost a couple points. Now this was interesting. You can figure this one out anyway. If you didn't have 23 degrees, some of you, where you got the sheet, it didn't have the designation. So, and I think only 2 people asked me about this. So it says, if it didn't have it at 23 degrees, if unsaturated air were to rise, what would the temperature be at 5,500 meters? Okay, so we have air going up. It goes up, it doesn't go up 1,000 meters, it goes up half of that. So if it goes up half of the height, it will decline in temperature by half the degrees. So there'll be a 5-degree difference. So you didn't need to even have this to answer this question. You could have said, if you had this, if you had this 23 degrees, and it rose 500 meters, so it rose half of this. Not 10, not 1,000 meters, just half. So if it rose a half, instead of 30, it'd be 25. It wouldn't be 20, because you didn't go up 10, you wouldn't have half of it. So it's half the degrees. So in this case, it would fall by 5 degrees. So the answer, if you had a 23-degree thing in, would be 18 degrees. If you didn't, you could do like one student did, and they say, or maybe more than one, say unsaturated air would rise, what would the temperature be? It would be 5 degrees less than when it started. Now that was a legit answer. You could say that. Some of you quoted other stuff that didn't address this. But it's unsaturated air, so you don't have to worry about, how much moisture is in it. But if that unsaturated air chooses to rise, and it only went up 500 meters, it went up, so it lost 5 degrees going up. So for whatever you started, if it's 23, it ended up as 18. Now this one, I have a note for myself to make adjustments in this one and this one next year. Well, this one's probably okay, this one. So the dew point temperature and the condensation level were 13 degrees. At what altitude would clouds begin to form? Well, that depends on where you start. They'd form at 13 degrees. So if you had this figure, 23, and assume that that was where it began, then this would be 1,000 meters. If you didn't have this, you wouldn't know about 1,000 meters. Because it didn't. If you didn't have this and think, okay, that's connected to this. So if you start here at 23, you go up 5 degrees, it'll be 18. If you start at 23 and you go up 13, that's 1,000 meters, drops 10 degrees in 1,000 meters, so that makes sense. That was what it would be. Because that's the condensation level. If it's 13 degrees, that's where it is. So however far that is from where you start, and if you use the 23, it's 1,000 meters. If you looked at the figure in 1710, with air beginning at 32 degrees, if you looked at that picture and said, okay, if that picture is what I'm looking at, then you could look at, and it'd be about 1900, because that's where 13 degrees would be. If it was 12 degrees, it'd be even, it'd be 2000, but otherwise, that was that. So if you gave me an answer, any kind of answer, I believe I gave you a point, but that would have been a little confusing. Because you need to know where it started from. This one you don't. This one you could work it out without knowing. This, it would, but a number of people got it. Most of the EC class got it. A number of you all got it. So people, yeah, anyway. Some people use this one, some people use this one. Both of them were right. If you gave me a reasonable answer, I would have kept it. Okay, why does the adiabatic rate? That's where you have cooling as a function of moisture in the air. The adiabatic rate, cooling change when condensation begins. Why does that happen? Because the latent heat released tends to retard the cooling process. It adds heat to the air. So that's why. The latent heat released tends to retard the cooling process. So you've got latent heat being released, and it slows the cooling process because it's adding heat to the air. That's why. And so because of this, the more moisture you have, the more latent heat you'd have being released. So that's why this is not a constant figure. The amount of latent heat released depends on the amount of moisture present. And because latent heat retards the cooling, the more you have, the more it'll cool. That's why you can get 9 degrees, generally, where you've reached the condensation level, but you don't have the moisture content is less. And here, if you got a lot more, then it goes down, it can go down to 5 degrees, so it slows down. This is 10, 10, 10, to that point 10, both up and down. But when you go above here, this condensation level, it can slow. It can slow from well, for practical purposes, we can say it slows from 10, from 9 degrees to 5. If you've got a lot of moisture in it, it's going to cause more heat to be released, so it's going to rise slower. It's going to drop slower. Drop slower. Okay? This, well, I said at the beginning of this section, and even before the section, I said this would be a tough one. And it is going to be. You're going to have to make an effort. If you've made kind of an average effort in this class so far, you're going to have to make a little bit more to get this clear. It just is, this is not so intuitive. And you're dealing with something that latent heat is not temperature. So, how do orographic lifting and frontal wedging act to force air to rise? So orographic lifting, we went through some of that. We just started to in the lecture last time. Orographic lifting is when air is forced over some barrier. It uses a mountain. It uses a mountain to say this is force, the air, like on the Pacific coast, you have the Olympic Mountains right on the coast. So air comes in off the ocean, Pacific Ocean, it forces them up. And that's why you get the rainforest. There's a Pacific rainforest, which is real heavy and dank. I mean, you can go 10 feet in and it's almost dark. Really heavy and dank. Moss, just real, suicide rate is high because it's so oppressive. Well, that's because air with a lot of moisture from the ocean is pushed up the mountain, and when it's pushed up, it comes to the condensation level and it rains. So they get an incredible amount of rain there. But then it goes over the mountains and down the other side. Well, it's already dropped a load of rain, so there isn't a lot of rain left. We're going to talk about that actually. We'll go into that later, but nonetheless. So that's where orographic living occurs, where air is forced over a topographical barrier. It's like a mountain, but it doesn't have to be a mountain. It doesn't go around the mountain, it's forced over it. Frontal wedging is where you've got a cold front and you got a warm front, and they come together, and so the cold front is denser and heavier, and it pushes the warm front up. And if it's really steep, like if it's shallow, and there's different reasons for that. If it's shallow, it doesn't push it up, and it's kind of more, you get a gentle rain. If it's steep, it cranks that thing up quick, and you get heavy rains like we just had. How does stable air differ from unstable air? Stable air doesn't want to go up. It likes to stay where it is. Doesn't like to be moved. But it can be moved, it can be forced up, but it doesn't like to. So it spreads out. It tries to hold on to where it was. Unstable air tends to rise vertically because it's lighter and warmer, so it wants to go up. And so just to note, stable air must be forced to rise, and so one would expect to see widespread clouds with little thickness, with precipitation to be light and moderate. Unstable air would rise and as a result tend to form towering clouds that generate thunderstorms and other severe weather. So, stable air probably wouldn't. Some light to moderate rain, but they're more flat and vertical. Stratus clouds. Unstable air would rise, the towering ones that you see, and they can generate thunderstorms and severe weather. Okay, what's the basis for classification of clouds? Their form and height, those two things. I think everybody got that. So, but to understand this, to be able to answer these questions, it would be important to do. To be able to answer these, I'll teach you 12. So, other questions on this? Now we're gonna talk about this right now. So we got to here yesterday, or Wednesday. Today's Friday. We got to here. So we had 3 mechanisms, they have 4 here, but 3 mechanisms, chief mechanisms for force lifting. You got convergence, where you've got things coming from each side, pushing up. You got orographic, which is pushed over here, and you got frontal, this is a front, this is a cold front that's pushing air up like this. And the cold front is denser. This would be a cold front, this would be a warm front. This is denser, so it stays lower to the ground. This is not as dense, so it would be moving up. And there are illustrations right here of that. Convergence. So this is the 2 flowing together. Air masses flowing together, colliding, generally resulting in upward movement, is a major contributor of stormy weather. In the Florida Peninsula, you got the Gulf, Mexico, or whatever President Trump calls it, and you got the Atlantic Ocean, and you got air moving can move from both directions, so over the central Florida, you get this thing happening when air is being forced up, and so you get serious rain in here. That's convergence, they're coming together, they're converging. Orographic lifting, this is using a mountain. But if this was a Pacific coast, this would be the Pacific Ocean. It's not warm, like it says warm ocean, that wouldn't be the Pacific, it's cold, but there is a Japanese current, so it's warmer than it would be otherwise. You have evaporation, you got winds coming off the ocean, getting this evaporation, and then the winds push the air upwards on the side of the mountain, and it reaches a condensation level, so you've got rain, 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 and it goes over the other side, and it's already dropped all its rain. So if it goes down, it doesn't have any rain to rain. Now, that doesn't mean that it doesn't rain in Seattle. It rains, used to rain when I was growing up a lot. But, generally speaking, this is typical. It'll drop most of its rain here, and then when it goes down the other side, this is a rain shadow, because it's dropped a lot of its rain over here, and doesn't have much to drop here. That's orographic lift. It doesn't have to be a mountain, could be any barrier. And frontal wedging, that's the one where you have the cold front and warm front. This is a cold front here, this is a warmer air, so this is moving and it pushes this warm air up.
Mr. Nelson?
Yes.
I think it was our last class period, and I have no track of time, so I don't remember when that was. We missed one under conditional instability because we were trying to go fast because the bell was about to ring. Can we go back up and look for that one?
Let me do that right after this class.
Okay.
It wasn't on the slide,
Oh, it wasn't?
there.
Okay.
so it's just,
Yeah,
this
so you
is
don't
the
have to
most
know that.
blank type of blank.
Yeah. So now you have these all written down. They're really light because it didn't print blue, I didn't want it to. Or I pressed the black and white button, so it didn't print blue, but it prints light. So you have all these. I thought I didn't have time to go through each one, and I'm not gonna stress on clouds. I want you to know a couple basic things about them, but I'm not gonna spend a lot of time expecting you to understand a lot about clouds. But you got cumulus, stratus, and cirrus, and those three, heat, clouds, layered, and wispy. So cirrus are the one real high ones. And then nimbus, when you've got nimbus by anything, it's nimbus would be, nimbus and alto would be things that you would connect with a type of cloud. Alto stratus, stratus nimbus. You'd have the combination names like cumulonimbus. Okay, that means heat clouds that produce rain. So cumulo up there, like cumulus, nimbus, they're heaping clouds, produce rain. Cumulostratus, which are heat clouds that join together in a layer, or cirrostratus, white wispy ones. So the basic names, cumulus are piled cloud, big puffy piled clouds. Stratus are more horizontal blankets of clouds. And cirrus are clouds that are thin, feathery, and tufted. They're usually really high clouds. What's that? I don't know if I can beat that up. Mare's tails and something. Mackerel scales and mare's tails. So those are really high clouds that look like little curls, not solid, but little curls way up. They're really high clouds. I forget what they mean, but that's a common way of designating, of referring to weather that's gonna come. When you saw that, so when you look at this, so if you were down here looking at things happening, you would see Sirius way up at the top, and cirrostratus, altostratus, nimbostratus. So these are the ones that would be bringing the heavy rain. You can look, and if you're cloud savvy, you can see by the kind of clouds what kind of weather you can expect coming. You see these real high, and say, okay, if you are aware that what the fronts are doing, you can say, okay, we can expect this to be happening soon. Clouds, okay, this is important. Well, everybody got this. Clouds are classified on their basis of appearance and height. That's what they're classified on. That's important to know. And they're basically, there are three basic forms and then additional ones. You have cirrus, cumulus, and stratus, and then one clouds of vertical development. Those are the ones that are very big, that generate the other, the more severe weather. These basic forms can be combined with each other, comprise about 10 distinguishable cloud patterns, and 4 general height classifications. High clouds are above 20,000 feet. Middle clouds are about 6,500 to 20,000. Low clouds are below 6,500, and clouds of vertical development can go up to 60,000 feet. They can just tower up there. And there's stuff going through in those clouds that are really serious. I think I mentioned the guys in the balloon, or guys in a glider went into a thunderstorm. Did I mention that one? Where they went into a thunderstorm? Well, the guys in the glider, one guy survived, but they were in this thunderstorm, and the wind can be 200 miles going up, 200 miles an hour. So these guys bailed out of this glider, and they were taken up and then dropped down. So they were taken up, froze, then dropped down, and then taken up again. I mean, they were going up and down. One of them lived. I don't know how he lived, but the others were just, it just became hail. Human hail. So if you're in a glider, don't glide into a cloud of vertical development, big way. Anyway. So, when air is cooled below its saturation point, it condenses and forms clouds. Clouds are a form of condensation. Clouds provide, what do they provide? A visible indication of what's going on in the atmosphere. Air movement, moisture, air stability, weather patterns. Clouds provide a visible indication of what's going on in the atmosphere. As a result of low temperatures and small quantities of water vapor found in high altitudes, the clouds are thin, white, and composed of ice crystals. So that's what mare's tails and mackerel scales, usually those are really high clouds, really very high clouds. Middle clouds, altitude clouds are thicker and denser because of greater availability of water vapor. Layered clouds generally indicate stable air because they don't want to go up, they just are flattened out. Clouds of vertical development are associated with unstable air. So if you had a question about what are clouds with vertical development associated with? Stable air, unstable air. Well, unstable air because they're going up. If it's stable air, they don't want to go up. Precipitation. Cloud droplets are really small. The diameter of a human hair is about 7.5 times larger than the average cloud droplet. Raindrops large enough to reach the ground without evaporating contain roughly 1 million times more water than a cloud droplet. So they gotta be big, relative to speed. Only temperatures well below freezing will ice crystals begin to form in clouds. There's different kinds of fog. So you've got this When warm, moist air is blown over a cool surface, the result may be a blanket of fog called advection fog. That's when warm, moist air, so you got warm air, it's blown over a cool surface, like water in the early spring. In the early spring, the water's still cold. It hasn't warmed up. The land will heat up faster than the water. So in the spring, you can have wind blowing over the land, which is warmer than the water, and when it hits the water, you get clouds forming. Because the water is colder surface, and it's like the bottle, like the AL8 bottle that was in the fridge. So you've got a colder surface, and the air around this colder surface can't hold much moisture. When you got warm air that can hold moisture come across, you got condensation, so you get fog, advection fog. I think that's a pretty picture. Radiation fog, I'll just read this, but formed on cool, clear nights when the Earth's surface cools rapidly. So cool heat escapes the Earth's surface. When it's cool, clear, and calm, as night advances, a layer of air in contact with the ground is cooled below its dew point, and it becomes heavier. So you see this here. You don't see it here. I see it here from my house, because I look out the window and I look up that valley, and you see fog flow forming. I mean, you can get out in the morning sometimes and see fog just hugging right the valley. It's really pretty. Radiation fog, upslope fogs, I'm not going to talk about that much. But this is steam fog. It's happening in where the water's warmer. So you can have the water colder, warmer. If it's colder and you got warm air coming out from across the land, that'll happen. If you got the water warmer and you got cool air coming on, same thing can happen. So it can happen for two different reasons. But you see this a lot. Driving into town, you see the steam rising a lot there. Okay. Convection air pressure. So we talked about this, speed at which air molecules move depends on air temperature. When an air parcel is warmed by the sun, molecules move faster, causing them to push outward as the air mass expands. Done? Okay. The expansion of an air mass causes a drop in density, and the air mass becomes lighter, which eventually causes the air parcel to rise. So that's the process. Heated by the sun, molecules move faster and push outward, air mass expands, it goes up. Cools as it rises adiabatically. As the air parcel rises, it cools and then eventually reach a point where it will become cooler than the surrounding air and begin to sink. So we're kind of imagining that we've got air in a nice little container. I mean, the air is all over. So it's not a nice container. We're talking about it in terms of a nice container because that's easier to think about it than it's just this swirling mass. Why the sun's heating of the atmosphere is not uniform? Because the surface of the earth, and we've talked about this before. The atmosphere, we've got texture, surface color, and material. There are three things that when the sun heats, like the sun will heat the asphalt at a different, and get a different result than they will on the grass or on the roof, or the different texture. So you got texture, color, and surface material. All those things affect that. We did talk about that earlier, so that's just a repetition. But atmosphere is constantly working to restore equilibrium, so air is moving from high pressure to low pressure. Now, everybody got that on the questions that we had before about this, but air is moving from high pressure to low pressure. So, you got two pressure, like out of a can. In a can, it's high pressure, you press it out, it shoots out, and it gets cold. It shoots out to the, it shoots out of a high pressure into cold pressure and expands quickly, which cools it. That's why when you press, like when you are, if you got a tire and you're letting the air out, you start to get condensation around the little thing when you press it in, because it's cooling the air and it's condensing on that thing. The air is cooling the air as it shoots out, it's cooling. It's high pressure inside the tire, but it's cooling out and pushing out and cooling. So movement of the air from one pressure area to different pressure is known as wind, and wind moves from high to low pressure. Factors affecting the wind. This is, you need to know this. Wind, put a star by this. Wind is a result of horizontal differences in air pressure. Air flows from areas of higher pressure to lower pressure. So we're not gonna do this a lot, but you've got things are measured in millbar. Well, we'll talk about that. Wind is nature's attempt to balance the air pressure. It's the unequal heating, oh man, is this ever important. It's the unequal heating of the Earth's surface that generates pressure differences, so solar radiation is the ultimate driving force of wind. There are things that drive the wind, but the ultimate driving source, ultimate, I have it in red there, ultimate driving force of is the driving force of wind, that's solar radiation, because it heats the Earth's surface, but it heats it unequally. It heats the water differently from the land, and different kinds of land, and in fact, different kinds of water. Chop water and other water is going to be heated differently, and so as a result, it generates pressure differences. And they are what generate winds. Okay, wind development. There's a couple of things here. An example of wind development, an island surrounded by cool water. Here's this picture, island surrounded by cool water. During the day, that little island is going to heat up faster than the water. Okay? This island will heat up faster. Sun down on everything. This water is going to take longer to heat up. This island is going to heat up quick.
Can you go up a little bit?
The island is going to warm up quick. So the air above the island is warmer. So you got warm air above the island, huh? And the air expands upward and outward from the island. This expansion of air lowers the air pressure at the island's surface. The cooler, heavier ocean air moves in towards the low pressure area over the island. So, when that heats up, it's like a furnace or a little stove in the center of this room. It heats up, and as it heats up, air rises, and colder air is drawn in. So you get, if you were on this island during the day, and it wasn't raining like it is now, you'd get a breeze coming toward the island, and it would circulate like this. If you could isolate it, you would see it circulating. You'd have cooler air coming in, heated up, and then like this. So it moves toward the low pressure area over the island. The result in a pressure gradient between the ocean and the island. Wind typically moves from high to low pressure area, and speed of the wind depends on the steepness, the differential steepness, that depends on the steepness of the pressure gradient. So different pressures. So there's lower pressure over this because you've got air going up, and so this heavier is drawn in and then heats up and rises, and you've got that happening. You can have the reverse happening, and we'll get to that in a minute. The lower the pressure, the hotter the island. So the hotter the island is, the lower pressure, and the steeper the pressure gradient and stronger the wind. So if this island hits up really hot, then you're gonna get a greater pressure gradient, you're gonna get a stronger wind coming in. Okay, you following? The pressure gradient provides a force that makes the winds blow. This force is called the pressure gradient force. That's not the ultimate. The ultimate source of wind is solar radiation. Well, there's 3 points. You get 3 points. So this is what we have, local winds. This is called local wind. And this is when you've got a sea breeze, a local wind is a sea breeze that forms much like the island. During the daytime, this land, sorry, that's nice. So the land heats up. So you get a breeze coming in off the shore. I mean, on Maui. I mean, working on the beach, building a condominium on the beach, couple condominiums on the beach. I mean, you had an onshore breeze. It was hot, but you had a nice breeze. Because the land would heat up faster than the water. So this would create a low pressure area over this, and so you'd have the higher pressure, the colder air drawn into land. So you'd get an offshore breeze. It's offshore breeze coming in, being drawn in and up, and so you get a situation like that. Like the island, except you're not on an island, you're on land. So if you're living by the coast, you can get that kind of activity because the land will heat up hotter or faster than the water. So the pressure gradient pushes the cool ocean air inland. The cool wind is a sea breeze. Over the land, air rises, then blows out to sea and sinks to replace it goes in that convection kind of thing. The airflow forms a complete circuit from sea to land and up, back to the sea and down again, and that's what we call the sea breeze circulation. The gentle sea breeze usually begins late in the morning. So that's when the land has been starting to heat up. You get a little breeze as it heats during the day. Would probably get an increased breeze. So it can reach inland pretty far. And at night, the land cools faster. So the water has been getting hit by the sun as well as the land. But in the evening, the land will cool off faster, so you'll get a reverse in this thing. So it'll go the other way. You'll get a breeze off the land that will go out because the water then becomes a low pressure area. It's warmer. And the high pressure of the land, because it's cooled off faster than the water, will blow out to sea. So the land breeze starts long before midnight and dies down after sunrise. It depends on the heating of the land or the cooling of the land. Mountain valley winds are local winds driven by buoyancy as well as pressure gradient. At night, a cold, heavy air sinks from the mountaintops into the valley. And narrow the valley, the stronger the breeze. Coming from the mountains, it's called a mountain breeze. These are hills, we don't get that so much here. But during the daytime, the warm air rises from the sunny mountain slopes. This rising air forms a valley breeze and blows up from the valley. So down at night, up during the day. Okay, the most important part of this really right here is the difference, the local winds, the onshore, coming onshore or offshore. Why you would have a breeze coming inland if you're on an island or on the coast, but say on an island, the breeze the island would heat up faster, and so it would draw the cooler air in. You get a breeze coming off the ocean and going up because the land is heated up faster. Then at night, when the land loses temperature faster than the water, you'd have a reverse. You'd have the land becomes cooler than the water, and so the water then becomes a low pressure, and you have the wind going out from the land toward the water. Monsoons. I used to go through a whole thing of this. I'm not gonna spend much time in, well, the most dramatic continental effects of wind and pressure occur on the Indian subcontinent. Here, the seasonal pressure changes from heating to cooling of Asia produces a complete wind reversal. During the winter, the sinking cold air over the continent flows outward toward the lower pressure, warmer air over the sea. The Indian Ocean is warmer than the continent, and you've got air coming off the Himalayas and all down across India, and that flows, and so you get air flowing outward to the Indian Ocean. And in the summer, the low pressure areas over the Indian subcontinent and Southeast Asia become centers of rising warm moist air from the surrounding waters. So that air comes in, it not only is drawn inland, but it brings a lot of moisture. And that lot of moisture ends up in manifesting itself in monsoons. So you get something like this. So in the summer, you've got the land is dry, it's gotten sun. This water is warm already, and so you've got high moisture coming in like this. Solar radiation heating up the land, it's drawn in, high moisture is drawn in, so you got incredible rains in the summer. In the winter, you've got it reversed. The water here, the high pressure is here, lower temperatures, this cools, this is still warmer than the land, so you've got it the reverse. The changing winds are called monsoons. Cold, dry winds that flow from cold interior to the winter monsoons, and then the summer ones, and they get, I forget how much they drop, how much rain they drop, but it's incredible. So you get people like this during the monsoon season, and kids playing and everything. If you know something about